Yeah, and then moment for our first presentation. Matthias, welcome.
You first to start. So,
You need to stop sharing here, though. Thank you, Dimitri, for announcing. This is good. Hi, everybody. Today, this is Anya. Today, we're going to talk about your favorite topic. That's right. Yeah? It's math. But I'm kidding. It's not this kind of math. It's going to be the cool kind of math that we're talking about, programmer math. We're going to talk about base number systems. It's going to be about 45, 50 minutes. This is how much energy you can ration for learning here. You can also take out your notes if you want to. And yeah, let's talk about number systems. We're going to learn about what number systems are, like base numbers. We're going to learn where they come from, what we use them for. We're going to talk about the code to convert those back and forth and deal with those. Mostly about binary and hexadecimal. Those are like the two big ones that we're using as programmers a lot. And we're going to look into how to deal with those in iOS, which I think is a really good topic. And at the end of this talk, or like 10 minutes into this talk, you're going to understand how this joke here works. Show of hands, who here has seen this joke before? All right, I want to say 20% maybe, not that many here. Who here of those understands this joke? Okay, of those, it's everybody. Cool. At the end, everybody is going to understand this joke. So first about me. Hello, I'm Matthias. I'm an iOS developer and freelancer. I do also Flutter and VR and AR, as you can see in these images here. Made my first step in 2011, back then still with Unity. And since 2015, I've been doing iOS apps full-time. This is a bit slow. Yep, come on. There we go. Also, I'm on Twitter and LinkedIn. Come connect with me. Would be cool to have you there. And these are some of the apps I've made, and I have currently in the App Store. It would be really cool if you can like go on there and give them like 4 or 5 stars. They'll be really nice. This is Standing's basketball widget. So the gimmick here is you can get your favorite basketball team scores on your home screen in a widget, which is like a niche that hasn't really been done that much, which I'm really proud of. And what we also have is Bluetooth Developer, my Bluetooth scanning app, which reached number 2 in the development app charts. Now, it says 96 right here. Like per day, it goes like up, down 100. Still really proud of it. Not happy with this here. But yeah, let's talk about math, base 10. So base 10, you all know, this is kind of our default base that we use. We count up to 10, and we have these numerals here available. This is what I call the alphabet, basically. So we start at 0, we go up to 9, and every number we have to assemble out of these 10 numerals here. So, you ready? Let's count. All right. Every programmer starts counting at 0, right? As you know. 0, 1. Who am I kidding? You know how to count. So we go up to 9. And now we've run into an issue because now we've run out of numerals to talk about, right? We want to show the next value higher here. What's higher than 9? But we don't have a specific icon for this anymore. So what do we do as clever people? And the thing that all of you know, of course, is that we then reset the rightmost value back down to 0, like here at the top. And one to the left, we increment by 1, right? It's easier to think of this, say there's 2 columns of numbers here going from the top to the bottom. We start counting with the rightmost one, increment, 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 increment. It's reached the end. We set it back to 0, and now we take the one to the left one further, right? And so on. The one to the left gets exhausted. No, the one to the right gets exhausted again. The one to the left, we increment another one up to 20 here. So far, so good. I'm going to start with the simple stuff, right? So you're like up to speed when we get to the complex things. And also, if we have a number like 123, we can decode what this actually means, right? We know, of course, this means 123 things. But we can actually decode the place values here. So the one on the rightmost, here in this case, this is the ones, right? This is 3 times 1. The one to the left, this is our tens. So this is 2 times 10. And the one even further on the left is the hundreds. So if we count all of these together, 1 times 100 plus 2 times 10 plus 3 times 1, we get 123. And as you've already noticed, probably, we can count these as values of 10. So the ones we count times 10 to the power of 0. As you experts already know, anything to the power of 0 is 1, right? So this is 3 times 1. The next one is 10 to the power of 1. So anything to the power of 1 is itself, so this is just 2 times 10. This one here is 10 to the power of 2, so this is 100. And if we go further to the left, we can say 10 to the power of 3, 10 to the power of 4, so we count from the right going into this. And as you also already noticed, we can express this as the base. So we don't count 3 times 10 to the power of 0, we count 3 times the base to the power of 0. And this is how we calculate the number out of this. But the question is, of course, why are we using base 10 specifically, right? Why not something else as a natural thing? And give you a hint, it's somewhere in this image here. You can see it, right? That's right, it's 10 fingers, right? This is how we do it in elementary school, how we learn this in kindergarten. 10 is a very human number. We're gonna come back to this image a few times. And now let's do the same thing again with a different base to show that we've all learned it. And I've picked an arbitrary base 3, because this is not something that's usually used that much, right? So let's start counting. I've done the base 10 here, 0 to 10, base 3. We start at 0 again, right? We go up 1. We go up to the next one, thank you. And now we have the same issue again that we have in base 10 when we reach number 9, right? We've exhausted our numerals. So the next one here is, as you already figured out, we go to 1, 0, right? The right one gets reset to 0, the left one gets incremented by 1. Let's just go through the rest one here. And we can also calculate this back again with the formula I just shown you. So 9 in base 10 and is 100 or 100 in base 3. And we can calculate this back saying, okay, this is 1 times the base to the power of 2. This is 0 times the base to the power of 1, and this is 0 times the base to the power of 0 also, which comes out to this is 9, this is 0, this is 0, 9 plus 0 plus 0 plus 0. Hey, check it out. This thing here in base 3 is this thing here in base 10. I think this is pretty sweet. You are now experts. Talk goes on for 30 more minutes. We're not done yet. All right. All right, let's talk about binary, finally. So binary, all of you know, and as programmers, this is bits. This is our base programming units. We usually tell this as we have a number 0 and we have a number 1 in our alphabet. Let's count again. Okay, we got base 10 to the left, 0 to 10. We got base 2 on the right. We start with 0. We do the 1 into the top, and we've exhausted our alphabet again, right? We are done here. So we do the same that we did down here, and we increment the right was 1 back to 0, and increment the one to the left by 1. Hey, check it out. In base 10, 2 is written as 10 in base 2. Isn't this cool? So now this increments the same way. We go up here. And you've probably seen this video here also. I've just implemented this here, where you can build a mechanical counter out of this, right? You always start counting on the right. Increment the thing. It's a bit slow, like we're sharing this via Google here, so this is like not full quality. I hope that's okay with everybody. You're going along? Cool, thank you. And then it flips over the one to the, no, okay, I skipped it, never mind. Let's continue. This is how it goes on. If we have like 4 digits here and all of these are 1, we get to number 15. Going on further, to 16, we have the 5th digit, and if we have 8 digits of this is going to reach number 255. Now, this is going to be important. I'm going to mention this in 12 slides or so again. Keep this in mind. We're going to come back to this. And now you understand how this joke here works. Who here understands this joke? I want to see full hand. Everybody raise their hand. If you didn't pay attention. Raj? Thank you. Now you also understand how this one here works, and they fucked up this one here. Because it's not 10, it should be 1, 0. And we can also write out binary in Swift code directly. So if you write a value prefixed by 0b, and then anything beyond this, this gets translated into binary integer in Swift pretty much immediately. So if you write 0b0, we get a 0 out of it. 1111, as we just said in the slide before, is 15. And this one here goes to value number 10. Now let's talk about base 16. This is the one also you're going to use the most as programmers. Everybody has probably seen this one. And now we have a different problem. Now we have a base that's higher than base 10, right? So we had base 10 at the beginning, and then we did base 2, which is just 0 and 1, and the base 3, which is 0, 1, 2. Now we have something that has more letters and more alphabets and more numerals than our previous 0 to 9, right? How do we deal with this? Well, we invent new numbers. Did you know that A is the 10 in base 16? We just start with the alphabet afterwards, like regular letters coming after 9. And if we go up to F, that means 15 in base 10. If we go up to 16, then we have the 1, 0 again. We've exhausted our alphabet. We're moving one further up. And interesting thing, if you have two characters exhausted here, if you have FF, this one comes up to 255. And as you're noticing, hey, hang on a second, 255, that was the maximum of 8 place values of 8 bits. 8 bits is 1 byte, as you know. So we can show the value of 1 full byte in 2 simple characters, which is like the main reason base 16 is used. And you've probably seen this in hex colors, right? So whenever you see something like this, which is a hashtag followed by 6 or 8 values that go up to F, like they start at 0 up to 9 through F, then it's a hex number. And what this basically means is we have the first two characters here, those are the red value, then we have the green value, the blue value, the alpha value, if it's 8. Alpha means transparency. And we can calculate the color out of this, which makes it very easy to transmit. So here we have a nice RGB chart. Let's look at navy here. This is a nice blue color. So it has 0 red components, 0 green components, and some blue components. So this relates to a blue color ultimately. If we take a look at the red one here, this one has some red components, some green components, some red, 0 green, 0 blue, and we get something red out of here. Black is fully zeros because it has no colors. White is fully white because it has maximum colors and everything. And if anything has like 3 times the same color here, that usually means it's a gray value because all of the color components are equally present in the thing. We can see this one again here. Say you have FF, that means maximum number of red, 0, 0 of blue and green. We get a red color out of this. You have 0 red, maximum green, 0 blue, it's going to be green. And as you know, in Xcode, we also have our nice color slider where we can pick those things, and here we get the hex numbers out of it. Turns out if you do full red and full green, you get a nice yellow out of it. And we can also write hexadecimal directly in Swift code. So you prefix this by 0x, and the number you're going to get out of there is going to be read as a hexadecimal number. If you do 0xFF, that's 255. 0x09, you're going to get 9 out of it, which is also pretty neat. What other bases do we have? We have base 12, duodecimal. This is a dozen, right? We use this one a lot. Surprisingly, shows up a lot of times, right? Considering we have base 10 anywhere. And here's also a thing, we also got to invent some numbers here. There's different spellings on this. You can write it AB. You can write it, this one here, this is a dec, and this is an elf. So this means 10 and 11 respectively. There's different spellings. And the benefit of base 12 is that it's supremely divisible, right? Base 10 is nice and all, but if you want to divide things by something else, you want to use base 12. So let's look at 50 here. 50, pretty nice round number, you would say, right? You can divide this by 1, 50, of course, 2, 5, 10, 25. But let's say you take a base 12 number instead, right? Let's say we take 48, which is a similar number, but in base 12. Now we can divide this also by 3, by 4, by 6, by 8, by 12, by 16, by 24. Base 12 is really cool. And it shows up a lot in our regular life. Now, where does base 12 come from? It's also hidden on this image here. Come on, somebody has to know this. From the what? No? Maybe? Maybe also. What are you pointing to? No, it's also not like, okay, time uses number 12, base 12, right? But it comes from somewhere in this image here. What are you holding up? Also not the in-betweens? Yes, it's fingers with 3 parts. Well done. It's the knuckles on one hand. This is 12. This is how in the olden Maya Inca times, people used to count the hours. And we got 12 on those, and it's starting at midday, 12 forward and 12 backward. So it turns out we thought base 10 was a very human number. Turns out base 12 is also a very human number. Who would have thought? Base 1, this is my favorite. Who here knows base 1? Raise your hand. I know it? Okay, plot twist. You all have used base 1 before. You all have seen it or used it at least. What base 1 or unary is this one here. You just make tally marks, usually. Has a downside. You cannot do a 0 with it. And really, you can do any symbol. It doesn't have to be a line. And I'm curious about base 8. Base 8 is octal. You can also use this one in Swift directly if you preface something by 0, O, which I think is a very complicated way to write it. Also cool, if you write something that's invalid, Xcode will tell you like immediately, okay, this is not valid. I don't know what octal is used for. Do you have any clue? Literally asking, I have no idea. I researched a bit, I couldn't find anything. Like binary, sure, hexadecimal, octal, I'm not so sure, but we have it as an option. Base 60. Where is base 60 on this image here? Okay, I'm gonna skip the asking, I'm just gonna show you. Base 60 is also on this image, which is our 12 knuckles multiplied by our 5 fingers. So we have hours, so you can have like times your finger, and you can go up to 60. So this is also a very human number, very natural to us. All right, what else we got? We got bases higher than 16. We have base 64. Base 64 we use for image encoding, especially in web contexts. You've also probably seen it. This is an image that's encoded in base 64. This is for a Shields IO badge you can put on GitHub, which I made a while ago. This is the Unity logo, which I ran through a base 64 converter before they put it in as a default one. You can also look it up on GitHub if you want to and put it in your project. We got base 85, which is even more encodings possible. We had base 160, even more encodings possible into a single character. Like if you want to cram a lot of information into those, you can get a lot out of it. Not going to talk about this as much. Talk about one of these would fill its own 45 minutes. There's base 248. I wrote this one wrong. I like this one here. This is made by web developer Quantum. He made a game called Hatris. And he wants to be able to share the moveset you did in one round with other people in a tweet. So Hatris is a game, it's a Tetris game which always gives you the worst piece possible, and then you're supposed to share your painful journey with other people with it. He invented base 2048 for this. Then there's also base 131,072. Theoretically, the highest base possible to use the entirety of the UTF space of safe characters, but there's only this many safe characters currently available. So this is still like theoretical. But in the future, there's going to be like more stuff added to it, presumably. Now, we still got to convert all of this. We're not done here. Let's do a test conversion from base 2 to base 10. So we start at 1101 from base 2, and this is going to be 13 in base 10. I'm going to do a bit cheating here. And the way we do this, we had this at the very beginning, is we take these place values and multiply them by our base to the power of the index counted from the right. So the index, the rightmost value is 1 times our base to the power of 0. Here we have to the power of 1, base to the power of 2, to the power of 3. And this comes out to 8, this comes out to 4, this comes out to 0, this comes out to 1. This is 13 in base 10. Or if you want to have this in a sort of formula, it looks about like this. If you have A, B, C, D, it's going to be B times base to the power of 2. You get it. This is how this looks in Swift code. We're going to go through this in a bit also because I made an entire program to run through this here. We start with our new number at the end. We go for our number string. This is the number we put in. The number has to be a string because it can contain various characters, right? It can be an A or an B or whatever we have in our base there. Then we get our current number value from that character, right? To have it into base 10 afterwards. So if this is a B in base 16, this is going to be the respective number in base 10. Get our exponent, this is counted from the right. Calculate this all out in one of these, and go through this ultimately through every single character. And now we got to do the conversion the other way. So we just did conversion to base 10. Now we're going to conversion from base 10 into any other base, right? So let's do 59 from base 10 into this number here in base 2. Also a bit cheated. We're going to give you the solution right now. And the way you do this, we got to do a while loop. We got to calculate our initial number divided by 2, and we're going to get the remainder out of it. This is going to be important here. This is the remainder. Then we take this value that we got out of it, divide that one by 2 again, keep the remainder, take this value here also, keep going with this until we've reached 0, and this sequence of numbers here, this is going to be our solution. So this one here reads 111011, 111011. Cool, we just got 59 in base 10, is this number here in base 2 in binary. So now we have the algorithm to calculate anything into base 10, and we can calculate anything from base 10 into any other base. And you've probably also figured out we don't really divide it by 2, we divide it by the base. And what we do here is we don't really take 0 or 1, we're using this numeral here as the index for our alphabet. So if this one says 0, we take the first value from the numerals we have available. If we have like hexadecimal, for example, this can have bigger numbers, and we're going to use one of these to assemble our number. And let's go through this in base 6, which we haven't done so far, right? So we're going to count again from 59 in base 10, this time to something in base 6. I'm not giving you the solution this time. And what do we do again? Okay, we divide this by the base. We divide this by 6, which is 54. The remainder is 5. Answer here is 9. 9, we go to the next one. We divide it by 6 again. This time it's 1. The remainder is 3. Now we divide 1 by 6. This is nothing. It doesn't fit in there. But we keep the remainder, which is 1. And now we take these numerals here and plug them in here. And 59 in B10 is 135 in B6. I know, it's very exciting. I can feel it too. This is how this looks in code. So we have our number here. We're going out from the case that we have a base 10 number that's valid, right? So we have our count remainder. We set it, remainder. We set it to the number we put in here. We get our base numerals, our alphabet. This is the number we get out of it at the end, right? This is the new base number as a string. And while our remainder is higher than 0, we divide this by our base. We get the modulo also, we get the remainder out of it. We use this result as the index for our numerals that we have available. So if this is base 16, then we have HF available here. And then we append this all to our string at the end, and we do a next iteration solution out of this. And we can also we actually have some pre-built functions in Swift to deal with this directly, which is nice because the pre-built function in Swift to do any number into an integer goes up to base 36. That one has 0 to 9 and A to Z as functions, or as potential inputs here. So if we put in the radix here as okay, we do this as an int. We put in the number we want as a string. Radix in this case means base. This is going to be a base 8, base 16, and this goes up to base 36. So if we put a Z character in there, that's going to be 35, because that's the highest value we can do with base 36. If we do the fabled 10 again in base 36, okay, this is the actual 36 here. And I wrote a program about 7 years ago to calculate all of these out, which we're going to go through now. There we go. Cool. Is this showing up? All right. This is my base converter, where you can put in any number, and you can convert any base from base 1 to base 160 including into any other base from base 1 to 160 including. And what we're going to look at here is, this is our basically the numerals, the alphabets we have available. This is base 64. This one, for example, starts with the letters of A to Z uppercase. Then we have the letters A to Z lowercase, then with the numerals of 0 to 9. And then we have the plus sign and the slash as further encoding. Base 85 follows different rules. This one has the numerals of 0 to 9 in there, plus these special characters. Base 160, this is my favorite. So we have numerals in here, we have our letters in here, we have our special characters in here. Then we have some Greek letters in there. And then we have some letters from the katakana alphabet, which is these ones here. So if you see any image encoding or any other encoding with these characters in there, that's got to be in base 160, which is also the matrix screensaver code, as you're realizing right now. So the way this works is we have our function. Actually, let's go through the examples here at the bottom. We can convert any string. We put it in as a string from a base we pass in to a different base. So 0 from base 2 goes to 10. Hang on, 0 from base 2 to base 10 is still 0. Actually, I want to run this one time. Should have run this before, really. And we have some other examples also here. We can do, for example, 13 from base 10 to base 2, which gives us out this number here in binary. Also works with negative numbers. There we go. All of these check out to be the same. We can also do stuff from unary. So this one here is our base 1, which goes to base 10, which is the number 4 that comes out of it. And this one also checks for some invalid input. Like if we give a base that's higher than 160, 161, this is not going to work out. And let's go through this right now here. I'm going to skip the housekeeping stuff. That's not interesting. So we need to convert any base that we put into here into base 10 first, so that afterwards we can convert this from base 10 to any other base. And if we go to a function that says convert any base to base 10, this is, here it is. This is what we looked at like 20 slides ago, where we have our number string. We go through there. We get the number value from this, so we can get the current character as an integer value. Let's look at the getNumber function, getNumberValue function, because this gets the current value from our numeral arrays. So we have, if it's a base 58, we use the base 58 array. If it's base 64, we use the 64 one. If it's anything below 58, we're gonna use the base. Hang on, how does this work? If it's 58, then it's 58, 64, 64. Those are special cases. Those must be the same. The bases in between, they are not defined. You can basically do your own if you want to. The way I'm using this is anything below 85 uses the base 85 numerals. Anything above 86 uses the base 160 numerals. Now let's go back to our function. We get our number value from there. We do the exponentiation, which we had earlier, counting from the right. If it's negative again, we multiply this by -1 to make it negative again, and we get our number out of it in base 10. Now we take that base 10 number we gotten out of here. Special case for base 1, if that's happening. It's looking good. Okay. Special case for base 1 if this is happening, and now we do this code here to translate this from base 10 into any other base, right? We had our while the remainder is higher than 0. We do the iteration solution here. Check at the end if something is negative, then we negate it, of course, again, and get that number out as base 10, which is pretty nice and much cooler than the standard Xcode input, Xcode functions that we have available. You can also check it out on GitHub if you want to and find some bugs and make a bug report, because there might be some. I just found one. You are now experts. Thank you. Any questions or compliments?
Did it have any unusual usage of numerical systems? I mean, like in usual cases we have with binaries, flags with specific colors.
Oh, I'd love to talk about these things in itself. Like talking about binary would be its own 45-minute talk with examples and layer masks and whatnot. And the base 248 one was the best one I found, where we encode this one game specifically. But really, there's not that many usages. It's just how much data can you get into a single one, into a single character.
you've asked about 8.
Mm-hmm.
So I'm not sure, but I believe that before we have 16s in our CPUs.
Mm-hmm.
We have the CPUs which use half bytes. So it's
Half byte is a nibble. That's an excellent theory. So we had a full byte is one hexadecimal number, right? There's also the half byte structure, which is very rarely used nowadays. There isn't an official name, but the unofficial name for a half a byte is called a nibble. Get it? It's a byte, it's a nibble. I like that theory. That's a good theory. That was what Octal is used for. Nice, thank you.
Also, everybody has a question how you come to this or these numbers. Maybe somewhere
Oh,
in
yeah.
the project or some networking, some
I know. I saw the algorithm 7 years ago, and then I went wild for like 2 days, and I was like, I'm gonna write the best algorithm ever. And then 7 years later, I'm gonna present it at CocoaHeads to a room full of people who are somewhat interested. And no, you're great, but it's a lot of math. I get it. I get slightly bit bored too. This is already the most fun version. Okay, that's enough for me. Thank you all.